So what we did was we look at the tricuspid regurgitation, because the only way you're going to get tricuspid regurgitation is if there's a pressure difference to force the blood from one direction into the other. So when you have tricuspid regurgitation, blood is flowing from the right ventricle across the tricuspid valve and into the right atrium in systole. So the gradient is the pressure difference between the right ventricle and the right atrium. So that pressure difference, so right ventricular systolic pressure minus right atrial pressure, that's the gradient. And the modified Bernoulli equation states that the gradient is equal to 4v squared, where v is the velocity. So if we look at our TR, and this is your tricuspid regurgitation, okay, so this peak velocity, okay, is what we're going to use. And we use the peak velocity, we square it, and we multiply it by 4, and that's the pressure difference between the right ventricle and the right atrium. That is what driving the blood across the tricuspid valve in systole. Okay, so pressure gradient, which is the pressure difference, is equal to 4v squared. So we're going to look at the next scenario, and when we talk about pressures, so if we talk about the pressure in the RV, we have a systolic pressure and a diastolic pressure. If we talk about the pressure in the PA, pulmonary artery, we're going to have a systolic pressure and a diastolic pressure. So remember, we established the fact that the right ventricular systolic pressure is the same thing as the pulmonary artery systolic pressure, unless you have some obstruction at the right ventricular flow tract or across the pulmonary valve. If you don't have any obstruction there, then the pressure, the right ventricular systolic pressure, is the same thing as your pulmonary artery systolic pressure. So that is your PA systolic pressure. Now, how can we calculate the pulmonary artery diastolic pressure? So you just have to think, I mean, it's basically, you have to conceptualize it and then use the formula to get it. All right. If you have pulmonic regurgitation or pulmonary insufficiency, pulmonic regurgitation or pulmonary insufficiency. So if you have PI, what you're saying is that blood is flowing backwards across the pulmonary valve from the pulmonary trunk into the right ventricular flow tract. So when you have pulmonic insufficiency, blood is flowing from the pulmonary trunk across the pulmonary valve into the right ventricular flow tract. That occurs in diastole though. That is a diastolic. So pulmonary insufficiency or pulmonic insufficiency is a diastolic problem. It occurs in diastole. Okay, remember in systole, you have normal forward flow. In systole, blood is going to flow from the right ventricular flow tract across the pulmonic valve and into the pulmonary trunk. That's systole. But when you have pulmonic insufficiency now, remember the pulmonic valve is supposed to be closed shut in diastole. It's supposed to be competent. But if the pulmonic valve is incompetent, then in diastole, blood is going to flow from the pulmonary trunk across the pulmonic valve into the right ventricular flow tract. That can only occur if the diastolic pressure in the pulmonary trunk is greater than the diastolic pressure in the right ventricle. You have to have a pressure gradient. For you to get blood flowing from the pulmonary trunk across the pulmonary valve into the right ventricle, there have to be a pressure difference in diastole. So that pressure difference is the pulmonary artery end diastolic pressure. That is the pressure in the pulmonary artery at the end of diastole. And you're going to subtract from that the right ventricular end diastolic pressure, because now we're talking about things occurring in diastole. So the gradient that's driving the blood across the pulmonic valve and into the right ventricular flow tract, that gradient is the diastolic pressure in the pulmonary trunk minus diastolic pressure in the right ventricle, the gradient. Again, remember, gradient is a pressure difference, and blood is flowing from the pulmonary trunk into the right ventricle. So the pressure in the pulmonary trunk have to be greater than the pressure in the right ventricle to drive blood in that direction. So that pressure difference, we call that the gradient. And from the modified Bernoulli equation, we know that the gradient is equal to 4v squared, where v is the velocity. So the gradient is equal to that, okay? So most of the time, we don't know the pulmonary artery end diastolic pressure. We don't know that. So if you rearrange the equation, your pulmonary artery end diastolic pressure is equal to the gradient plus the right ventricular end diastolic pressure. Okay? In later lectures, I'll tell you how you can get the right ventricular end diastolic pressure, which is the same thing as the right atrial pressure. Okay? So your right ventricular end diastolic pressure, same thing as the right atrial pressure. But we have a separate lecture to go over that, and I'll show you how we get that. So your pulmonary artery end diastolic pressure is equal to the gradient, which is 4v squared, plus your right atrial pressure. This pulmonary artery end diastolic pressure is somewhat elusive, and we can't readily get it. So if you can calculate it using hemodynamics, great. I just showed you how to get your pulmonary artery systolic pressure. All right? All right, so let's move on. So on top, we have a two-dimensional echo. This is a short axis at the level of the aorta. This is your transducer. The cursor is across the pulmonic valve, and you do your P doubler or C doubler. You do C doubler. You know, when you're doing these things, you need to do C doubler. So you do C doubler, and you get this envelope. If you remember clearly, this is your pulmonic insufficiency envelope. Okay? This is your PI envelope, pulmonary insufficiency envelope. Okay? It's diastolic. Remember, systole is from the beginning of the QRS to the end of the T wave. Diastole is from the end of the T wave to the beginning of the QRS. So this envelope is a diastolic thing, which is what you expect. It's pulmonic insufficiency. The velocity you're going to use, though, is your end diastolic velocity, this one right here, your end diastolic velocity. You can see there are two velocities. There's a early velocity and there's a end diastolic velocity, okay? So this is the one you're going to use. And then you plug that in your equation, okay? Remember, gradient is equal to 4v squared using modified Bernoulli equation. Okay, you always have to remember that. Okay? So, again, the gradient is equal to the diastolic pressure in the pulmonary artery minus the diastolic pressure in the right ventricle. The gradient is equal to 4v squared. So when you plug all of that in the equation and you rearrange the equation, your pulmonary artery end diastolic pressure is equal to 4v squared plus right atrial pressure. All right? Again, you have to follow that. Okay, so we can use the combination of the modified Bernoulli equation and understanding what's happening across the different valves and chambers to calculate pressures, because we can use the modified Bernoulli equation to get the gradient, and then we can calculate the absolute pressure in any one of the chambers if we know the other one. All right, let's look at left atrial pressure. So we showed you how to get right ventricular systolic pressure. We showed you how to get pulmonary artery systolic pressure, and we showed you how to get the pulmonary artery end diastolic pressure. Now we're going to look at the left atrial pressure. Left atrial pressure, if you remember clearly, when we spoke about diastolic function and dysfunction, the left atrial pressure was very, very prominent in the gradient of diastolic dysfunction. Grade 2 and grade 3 diastolic dysfunction, you have elevated left atrial pressures. So knowing how to calculate left atrial pressure is very, very helpful. So if you just think about it a little bit, when you have mitral regurgitation, so let's conceptualize what mitral regurgitation is. Mitral regurgitation is the backflow of blood from the left ventricle across the mitral valve and into the left atrium. That is mitral regurgitation. The normal flow of blood would be from the left atrium across the mitral valve into the left ventricle. But when you have mitral regurgitation, you have flow in the opposite direction. From the left ventricle across the mitral valve into the left atrium. So you have to have a pressure difference. If blood is going to flow in that direction, the pressure in the LV must be greater than the pressure in the LA to force blood in the opposite direction. That pressure difference is what we call the gradient. The pressure in the LV minus the pressure in the left atrium, that is the gradient. LV, and remember this occurs in systole. So the LV systolic pressure minus the left atrial, if you want to call it systolic pressure, is equal to the gradient. Modified Bernoulli equation, gradient is equal to 4V squared. The gradient is equal to 4V squared. So we're talking about mitral regurgitation. So the velocity we're talking about is the peak MR velocity. So if you rearrange your equation, you can get left atrial pressure, and your left atrial pressure is equal to the LV systolic pressure minus the gradient, which is equal to LV systolic pressure minus 4V squared. Of course, V is the velocity of the MR. But how are you going to get the LV systolic pressure? Yeah, you can puncture the left ventricle and measure the pressure directly, but the patient is going to be compromised. You can put a catheter in the LV and measure the pressure. I mean, that's an invasive approach. But the blood pressure, when you do someone's blood pressure, the systolic blood pressure is the same thing as the LV systolic pressure, the systolic pressure in the left ventricle. So when you do someone's blood pressure, the systolic blood pressure is usually the same thing as the LV systolic pressure, unless you have some obstruction across the aortic valve or the left ventricular flow tract. The systolic blood pressure is the same thing as your LV systolic pressure, unless you have an obstruction across the aortic valve or the left ventricular flow tract. Okay? So you just substitute the systolic blood pressure right there. You do your MR. So, okay, so two-dimensional echo is on top. Your transducer is right there. This is actually a two-chamber view. You can use it, okay, where you have, this is your two-chamber view. So your left ventricle is on top, okay, and your left atrium is on bottom, okay. When you have mitral regurgitation, the blood is going to flow from the left ventricle across the mitral valve into the left atrium. It's moving away from the transducer, and it's going to be below the baseline. It's a systolic phenomenon. So systole is from the onset of the QRS to the end of the T wave. So your envelope is going to be below the baseline, and it occurs in systole. The velocity we're talking about is the peak MR velocity, and in this case it is 5.54. So if you square that, you multiply it by 4, and you plug it in the equation, you can calculate your left atrial pressure. Left atrial pressure is equal to LV systolic pressure minus 122. So once you remember the LV systolic pressure is the same thing as the systolic blood pressure. Same thing as the systolic blood pressure, unless there's some obstruction across the left ventricular flow tract. So you can use MR to get your left atrial pressure. And again, remember, left atrial pressure is very important. It helps us to grade diastolic dysfunction. Okay, so similar to our PA pressure, where we were able to get PA systolic and PA diastolic pressure, we can also get your left ventricular end diastolic pressure. So again, when we talk about any pressures, you're going to have systolic, which is on top, and diastolic, which is below. So we can get our LV systolic and diastolic pressure. Okay. Remember, this LV systolic pressure, same thing as the blood pressure. So we got our left atrial pressure. We showed you how to get that. We're going to show you how to get your left ventricular end diastolic pressure. Left ventricular end diastolic pressure. And again, a little bit of concept and using the modified Bernoulli equation. So when you have aortic insufficiency, blood is gonna flow from your aorta across the aortic valve into the left ventricular flow tract and into the left ventricle, the opposite direction to which it normally flows. Again, when you have aortic insufficiency, blood is going to flow in the opposite direction to which it normally flows. Blood normally flows from the left ventricle across the left ventricular flow tract, across the aortic valve, and into the aorta. That's the normal forward flow. But when you have aortic insufficiency, blood is going to flow backwards. It's going to flow from the aorta across the aortic valve into the left ventricular flow tract and into the left ventricle. And that is occurring in diastole, because remember, when the LV contracts, that's systole, and it's going to force blood forward across the left ventricular flow tract, across the aortic valve, and into the aorta. That's a normal forward flow. In diastole, the aortic valve should be competent and should not allow blood to flow backwards. But if the aortic valve is incompetent for whatever reason, in diastole, blood is going to flow from the aorta across the aortic valve into the left ventricular flow tract and into the left ventricle. So we can use AI. We can use AI to calculate our left ventricular and diastolic pressure. So in diastole, if you have AI, what I'm telling you, or what is occurring, is the diastolic pressure in the aorta is going to be greater than the diastolic pressure in the left ventricle in order for you to get blood to flow from the aorta, cross the aortic valve into the LV. The pressure in the aorta have to be greater. If the pressures were the same, you wouldn't get any flow. There wouldn't be any gradient if the pressures were the same. But because the pressure in one chamber is greater than the other pressure, you're going to have blood flow in the direction of the lower pressure. Okay? So that gradient that we're talking about, which occurs in diastole, is your aortic diastolic pressure, because blood is flowing from the aorta into the LV. So it's the aortic diastolic pressure minus the left ventricular end diastolic pressure. That's the gradient. And as we have been saying over and over, gradient is equal to 4v squared. In this case, let me show you which velocity. So again, when you do AI, you put your cursor across the aortic valve and you get this envelope above the baseline because your transducer is there, aortic insufficiency, blood is flowing from the aorta, across the aortic valve into the left ventricle, it's flowing towards the transducer, hence the flow is above the baseline. And you have an early velocity and a late velocity. The velocity we're talking about is your end diastolic velocity. End diastolic velocity. Okay? So what you do, you square this velocity, multiply it by 4, and that's the gradient. Gradient is equal to 4v squared using the modified Bernoulli equation. So again, if you're real, okay, so let's go back to the original equation. Okay, so the gradient is equal to the aortic diastolic pressure, because blood is flowing in the opposite direction, minus the left ventricular end diastolic pressure. Usually, this is what we can measure. This is what we can't measure. So if we rearrange the equation to get the left ventricular end diastolic pressure, which is equal to your aortic diastolic pressure, and what I'm going to tell you is that the aortic diastolic pressure is the same thing as your diastolic blood pressure. Again, the aortic diastolic pressure is the same thing as the diastolic blood pressure. So if you remember, and the gradient is equal to 4v squared. So your aortic diastolic pressure minus 4v squared, that's your left ventricular and diastolic pressure. Okay? All right, so left ventricular end diastolic pressure is equal to the diastolic blood pressure minus 4v squared. So you get this velocity, your end diastolic velocity, you square it and multiply it by 4, and you get your left ventricular end diastolic pressure. Okay? So let's stop here, and then our next session, we will discuss additional topics in hemodynamics.